All right, Bismillahirrahmanirrahim. Let's start recording. And here we have a numerical, which is the crane can be adjusted. Okay, the crane can be adjusted for any angle theta greater than or equal to 0 and less than or equal to 90, and any extension x greater than or equal to 0 and less than or equal to 5 meter for a suspended mass of 120 kilograms. Determine the moment developed at A as a function of x and theta. What value of both x and theta develop the maximum possible moment at A? Compute this possible movement. Neglect the size of the pulley at B. Okay. Now if you look at it very carefully, this is a crane, a very common example. You can see in the industry somewhere where the construction is been going, and any type of industry where there are heavy loads are involved. These cranes are used in construction of roads, construction of bridges. These cranes are very much used. Okay, so from the practical example point of view. So this crane basically has got a length of its beam as 9 meter, and then there is a boom which is extending from it. Its length is x, and x has basically got a limit of from 0 to 5. 0 means the booms goes totally inside, and 5 means it's the maximum it can go outside to increase the span of the crane. Okay, so and then there is basically from A till the end to that pivot point, it is like 1.5 meter. Then pivot point A, the beam has some 9 meter beam has an angle of theta. Okay, and that theta is also been given the min and max limits from 0 to 90. Okay, and then there is a weight of 120 kg, and then there is basically a piston sort of mechanism that is basically being used to lift this crane. So how are we going to use this? We are going to use it as first of all, we shall be interested in the movement, the maximum possible movement. If you look at it, the maximum possible movement from B, it's still point A. Okay, so from even behind that A, but we are clearly given that point A, and we want to be interested in the maximum movement at A as he asking us in the question. So what we do is we calculate the moments at A with the force acting at B. So if you look at it, the weight is 120 kilograms. To convert that weight into kilograms, we need to multiply it with 9.81, and then basically this is the force. 120 kg into 9.81 gives you the force. Then we need a perpendicular distance. If you look at the perpendicular distance, how would you say? The perpendicular distance will be not along this length from B to A, but it is perpendicular distance will be something like force, because if we go from B to A, that will not be, that will be some angle from here. So we want it at 90. So what we will do is basically we will basically say the perpendicular distance will be this is 9 meter, and the effective length is from A is comes out to be 7.5, and then there is this length is x, so it will be 7.5 plus x, but we want a perpendicular distance, so that will be some angle from B to the straight line here till the A, so it will be 7.5 plus x cos of theta. Okay, now then we go multiply it by 120 and then why is the minus sign coming? The question is minus sign is coming because since see the crane is fixed at A and this weight is acting downwards. So since the crane is fixed at A, this B, this force is going to see if you see my mouse cursor, it's going to take it in which direction? It is taking us in the clockwise direction, and since it is taking us in the clockwise direction, it will be a negative sign. Okay, so you multiply 120 into 9.81 and you will get 1177.2. cos theta into 7.5 plus x. Okay, and then basically what you do is basically 7.5 plus x, and then simplify it further to 1.118 cos theta, make Newton meter into kilonewton meter clockwise. Now we have to look at this function has been generated for moment at A, in which our two variables are there. You can change what are those two variables in this question. If you look at it, the one is the x and the other is the theta, the x and the theta. So the maximum moment, he is not asking for the moment, there will be moment. He says in the question that the maximum possible moment. So for the maximum possible moment, we will write it as theta is equals to 0 degree. If you look at it, why is theta 0 not 90? Because you know, to take theta equal to 0, because if this is the maximum possible value, and the other is basically because you know this is cos theta, and if we say cos 90, it will become a 0. And for increase x equals to 5, why not 1, why not 2, why not 3? Because you want to increase your momentum. So if we want to increase our momentum, we will write it as x equals to 5. Now you put these values of theta and x equals to 5 into your equation. 1.18 cos theta, 7.5 plus x kilo Newton per meter. If you put on these values, then you can very easily calculate the maximum possible moment, and that will be minus 1177.2 cos theta. Cos theta becomes 0, and 7.5 plus for x we put equals to 5. We simplify it, and we get minus 14715 Newton meter. To convert it into kilonewton meter, we write it as 14.7 kilonewton meter, and minus sign here was here, but we do not put here because we already write clockwise, and clockwise means it's negative, so we do not need to put a minus sign. If we don't put clockwise, we can put negative sign. Okay. Let's go to another numerical. Determine the movement of the force at A about point O. Express the result as a Cartesian vector. Okay. So there is a force which is acting at A. If you look at it, you need to find the movement of this force at A about the pivot point O, and your result should not be a scalar, but they want the result of the movement in the Cartesian vector form. Okay, so how are we going to do this numerical? If you look at it, we are going to do this numerical like this. Is the force is 60I minus 30J minus 20K Newton. Okay, this is your coordinate system. First of all, we need to find the origin coordinates of the origin. Origin coordinates will be x0, y0, z0. What will be the coordinates of point A? The coordinates of point A can be very easily calculated, as if we move here on x-axis to point A, it will be a 0. We are not moving in x-axis. What about the if we move on the x-axis, it will be from origin. If we go to this point as it will be minus 3, because this is the origin. If you go back, it will be on the negative side. So minus 3. What will be the y-axis? It will be minus 7. If we go from minus 3, minus 7, and from here we go above. And how much is it? Is 4 meter. So we can take a position vector from basically OA. So when we take the position vector OA, we will basically subtract the coordinates from of A to from A to O. So when we subtract the coordinates, it will be minus 3 minus, for our position vector ROA, it will be minus 3 minus 0I plus minus 7 minus 0j, and for the vertical Z components it will be 4 minus 0k meter. So ROA comes out to be equal to minus 3I minus 7j plus 4k meter. Okay. Then we go for the movement of the force about point O. Since he is interested in the movement, not scalar but Cartesian, we know the formula from the previous lecture. We know the Cartesian vector formula for movement is MO is equals to R cross F. Movement from any point O is equals to R cross F. Here R will be the position vector ROA that we taken from O to point A. So IJK ROA is what? Minus 3I minus 7J plus 4K. And what is going to be the F? He has given the F in the numerical as 60I minus 30J minus 20K. 60I minus 30J minus 20K. So it comes out to be equals to MO is equals to ROA cross F. So it is 260I plus 180J plus, you simplify determinant manually, or it's very easy. I will be allowing you can use your scientific calculator. There is, you can easily insert the values of R minus 3 minus 7 4 and the values of F 60 minus 30J minus 20K. So you will get this movement as ROA cross F equals to 260I plus 180J plus 510K Newton meter. Now since this value of movement is in the, has the components I, J and K, so this movement is not a scalar movement. Because of I, J and component, it is a vector movement, and then when it is vector because of I, J, K, it basically satisfies this what is asking in the question, express the result as a Cartesian vector. So this movement M naught is now a Cartesian vector. Okay, is it clear? That is very good. We will move to the next numerical. Express another question, a good question. Determine the movement of the force F at A about point O. So you need to determine the movement of the force F at A about point O. Express the result as a Cartesian vector. Okay, so if you look at it very clearly, this is the force 13 kilonewton. Remember, it is a very similar question than the previous question. What is different in this numerical compared to the previous one? The force is the variable thing compared to the, is different from the previous one. From the previous one, they have made our life very easy by giving us the force in a Cartesian vector form and asking the movement in the Cartesian vector form. But this numerical, if you look at it, is different because they give force in scalar form. And since they are giving the force in the scalar form and are also asking the movement about O in Cartesian vector form. So one thing we have to do different from this numerical is we also have to convert this scalar force into the Cartesian vector force, and rest all the numerical is simply the same as the previous one. So what we do is basically, this is the origin coordinates, then we calculate the coordinates of A. If we calculate the coordinates of A, it will be very simple, and that is basically, if you look at it, A is will going behind the origin as minus 2.5, and we go in the negative y as minus 3, and then we go positive as z as A. In A is 6 meter, and what are the coordinates of the B? If you look at it, we go from the negative x as 4 meter, so it will be minus 4 meter. And then basically we go in the y-axis is the positive y is 3 meters, and x is minus 4 meters, and the z is the, if you look at the z, it is the 8 meters. All right. So the coordinates will be -4, 3 plus 8. So we can subtract the coordinates of B from the coordinates of the A. So if you look at it, the x coordinates, if it's -4, because B coordinates minus A coordinates, x coordinates will be -4 minus 2.5. So your first x component will be -4 minus 2.5, minus becomes plus, so it becomes as -1.55. Similarly, j will be +6j plus 2k. Now we want also the mod of RAB. So we have done RAB, and what will be the mod of this RAB will be, it will be -1.5 the whole square plus 6 the whole square plus 2 the whole square. So RAB comes out to be equals to 6.5 meters. So now we want, we have done the RAB, which means this is enough we have done for the force 13 kilonewton to be converted into the Cartesian vector form, because this RAB components, RAB will be basically transforming into the force. Okay, so if you look at it very carefully, just the force components to transform it is basically what they have done over here is that the force is 13 kilonewton. Here it is 13 kilonewton. Its S component will be -1.5 divided by 6.5. Then the Y component, its magnitude total is basically 13 kilonewton, and the Y component will be 6 upon 6.5. And then for the K, it will be again 13 for the force, 13 kilonewton, and the Z component will be 2 divided by 6.5. So this, multiply this, we will get the force in Cartesian vector form. Now the previous thing was basically he is interested in the moment about O. So we take the position vector ROA. So the position vector ROA means coordinates of A minus the coordinates of 0 of origin O. So it comes out to be -2.5 -3 plus 6. Okay, now this is again our determinant is complete for the moment about O. Now again I give you the same freedom. You can either simplify this determinant, or basically you use your scientific calculator, you insert the values for ROA and you insert the values of, first multiply all these values, multiply and divide respectively to get the force values, and then basically you multiply, you simplify this determinant. If you do it correctly, you will get your movement in the Cartesian vector form, and it will be -84i minus 8j minus 39k kilonewton meter. So this will be movement about O in this. You can also basically, this is MO equals to ROA cross F. If just at home, if I say, you can make another question out of it just to gain more knowledge. If I say calculate the movement in exam, movement of force F at A about point O. No, I don't want to. I say calculate the moment of force F at A about point P. Where is this point P? Express the result as a Cartesian vector form. So things all remains the same. But for since the moment is calculated about P and not about OA, so we will take a position vector ROA. No, it will be for this numerical, for the later one it becomes RPA. You will take the position vector RPA, coordinates of P minus the coordinates of A. You will be taking this, like this you will be doing it. Okay, so you will be taking not ROA but rather RPA. Okay, so you will be doing it like this and you will get movement at P. So same numerical, just a little bit of variation is to calculate this position vector OA changes to RPA, and the movement will be slightly different compared to the movement at O. Okay, let's go to a new topic. Okay, movement of a force about a specified axis. Okay, if you look at this picture is very common. If you go to Kimadi, where ships are docked or where the commercial ships are being docked, you will see cranes like this very commonly if you go to Port Qasim or you go to Kimadi port. Okay. So what does he says? If large enough, this cable force F on the boom of the crane. Okay, where is the boom of the crane? This is the boom of the crane. Cause the crane to topple over. Okay, they say if this force is very large, this huge force can topple this crane, which means it can break it from the base, these four legs, and it can come basically topple down upside down. Okay, so this is very important. So to investigate this, the movement of this force must be calculated about an axis passing through the base of the legs at B. So since this, even though this force is huge, you have to basically lift it, to do it correctly, if we have to calculate the movement of this force through the axis which is passing through A and B. So this is a very practical example in real world problems. Not doing it correctly, if we move a little bit on one side or the other, front or back, this crane will lose its structural integrity and it will basically fall down with the luggage and with whatever containers it is lifting. So very important and very dangerous if you do not calculate it correctly. So movement of a force about a specified axis. Sometimes the movement produced by a force about a specified axis must be determined. For example, suppose the lug nut at O on the car tire, they're saying there is, these are lug nut on the car tire is there, you need to loosen it. Okay, so what happens that you are going to apply a force over here, and because of that force there will be some movements generated in a three-dimensional axis, and this movement generated will have its different components. It will have a component along say x-axis because it's a three-dimensional scenario. It will also have a component along y-axis. It will also have a component along z-axis. So in very easy terms, this will always be there because the force is creating a movement, and that movement has some ijk components along x, y and z. But when we look at it, since we are opening the nuts of our wheel of our tire, if you look at it, we have, this is x-axis and this is z-axis. We will not be, even though the movement will be there, but we will not be interested any movement on which is acting on x-axis or the movement which is acting on z-axis, even though the movements will be there because of this movement axis m naught. It will have components along x and components along z and y, but our entire focus and our interest will be the movement about the y-axis. Why? Because these nuts, when to be taken out along the y-axis, or when we tied those nuts, also it will be along the y-axis. So we will have our entire interest on the y-axis, and we disregard or not take into consideration the movements about the component of movements about the x and the z-axis. So this is basically in a crux the story what is trying to tell us over here as movement of a force about a specified axis. Let's go to another problem, vector analysis. To find the movement of this force F about y-axis using vector analysis, we should determine the movement of this force about any point O on the y-axis. Okay, so we need to calculate the movement of this force about the y-axis. For example, the same thing is doing, he's applying this force F, and a movement will be generated as r cross F. What is he saying over here as this equation, standard equation, always remember m naught is equals to r cross F. So the component my, what is he saying, this component my along the y-axis is the projection of m naught, this m naught projection along the y-axis. Okay, it can be found using, इसको हम कैसे निकालेंगे, using the dot product डिस्कस इन चैप्टर 2. हमने डॉट प्रोडक्ट आपको बताया था कैसे, किसके एडवांटेजेस मैंने बताए थे अपनी, याद है पहली जो हमारी स्लाइड थी उसके अंदर. सो वी विल टेक द डॉट प्रोडक्ट in order to calculate this moment y, which will be j naught r cross f, where j is the unit vector on the y axis. Okay, So in simple terms, if you basically consider it, a new mathematical term will generate. So generalize the approach by letting UA, what is it saying? UA be the unit vector that specifies the direction A axis. Okay, that is specifying the direction for direction A axis shown. Then the movement of F about the axis is move about MA, which is basically about this axis. Is trying to say MA is equals to UA dot R cross F. So you take what UA is the unit vector about this axis. What is it trying to say? And you take a dot product and you do the cross product, the vector product of R cross F, which was this M naught. This is M naught and this is UA. So you take a dot product of this with the vector product of M naught. So this combination is referred to as the scalar triple product. If the vectors are written in Cartesian vector form, we have, again, if you write these vectors in Cartesian, because this was the unit vector UA. So unit vector UA will have three components, UAXI plus UAYJ plus UAZK. Then he says you have to have a dot. This is the dot, and then R cross F can be written as this determinant IJK, RX, RY, RZ, FX, FY, FZ. So this gives you the movement at A is equals to AXY, UAYJ plus UAZK dot R cross. If you simplify this relation, you solve this determinant and you take the dot product after solving this determinant with this three-dimensional unit vector, and you take the dot of the two, you will be basically getting this term. This term can easily be further written as and simplified as like this UA dot R cross F. You can write it like this: UAX, UAY, UAZ, RX, RY, RZ, FX, FY, FZ. Remember, when you take a scalar triple product, it will not be here you will see the simple vector product is IJK, RX, RY, RZ, RFX, FY, FZ, but for a scalar triple product it comes out to be UAX, UAY, UAZ, RX, RY, RZ, FX, FY, FZ, where UAX, UAY, UAZ represents the XYZ components of the unit vector defining the direction of the A axis. RX, RY, RZ are the position vectors, RX, RY, RZ extended from any point O on the A axis to any point A on the line of action of the force. Okay, FX, FY, FZ. Okay, so he's saying Fx, Fy, Fz are the components of the force vectors. So you look at it over here. Further, they're trying to explain you. This is basically from O. This is R. This is F. This is any point A. What is he trying to say? And then basically from this point O, if any axis is passing, this is the A axis that is passing here. If you look at it, this is the AA axis. So what you do on this A axis, since it's passing to this point O, we take it as that standard axis for UX, UY, UZ, and then basically they solve for R cross F. Okay. So when MA is evaluated, it will yield a positive or negative scalars. Okay. So movement can be a positive or a negative scalar, indicates the sense of direction MA along the A axis. Okay. So if it is positive, MA will be the same sense, whereas if it's negative, MA will be the opposite sense. Very simple. Okay. Okay, the pipe assembly is subjected to the 80 Newton force. Okay, so this is a very important numerical and often comes in sometimes in midterm and often comes in the exam also. So a good and a very technical type numerical, often used a lot practical oriented example. Okay, numerical. The pipe assembly is subjected to the 80 Newton force. Determine the movement of this force about point A. So this assembly is subjected to the 80 Newton force. You need to determine the movement of this force about which point? This is the point A. And where is the force? This is the force which is 80 Newton. So F is equals to 80 Newton. Here they are saying, see, in the 3-dimensional this force is acting, and it is a 3-dimensional space force. Why it is? Because it is in a 3-dimensional plane, not in XY axis or YZ plane, not in XY plane, not in XZ plane. Okay. So the force is acting at C, and the movement effect is to be taken it as at A. So how to solve it? The question arises. Like the previous two numericals that we have done, we can apply the same concept here also, and that concept will be that we need to calculate the coordinates of A, which is going to be 0, 0, 0, and we also need to calculate the coordinates of C. So if you look at it, how we will calculate the coordinates of C, it will be, if you look at it from here, you go to, from here x-axis it will be 300, and then also here straight distance is 250. So 300 plus 250, it will be 550. So 550 means 0.55. And what will be the y-axis distance? It will be from here O to, if you move here till point B, which is lying exactly at C, it will be from here to here, it will be 400 mm, so 0.4. And what will be the K component? If you look at it, this is the same plane. When we go down, it is 200 mm, but below Z is minus 200, so it comes out to be minus 0.2. So we take a position vector AC and we cross it with the F. We basically cross it with the F. So we have to take the, calculate the position vector AC. That means RAC cross this F. But there is a problem. The F is not in the Cartesian vector form, but they have given us it in the scalar form. And the problem is not stopped here. They have further made our life more difficult by giving us this force in respective angles of space. And what is this means? That if you look at it, this force is making some angle in your x and y axis, some angle in along y and x components, and then it is going below some angle 30 in z axis, and it's making angle some x and y axis in xy plane, 40 degrees angle. So F will be, if we want this force 80 Newton to be transformed into Cartesian vector form, which means it have ijk components. So how we will do it? You have to basically do F is equals to 80 Newton. Here 80 Newton. Then what you do? You calculate the I components. For I components, it will be first going at as if you look from 30 degrees, it will be, you see this triangle from here, this triangle and this triangle. So this triangle will be a cos component. It will be cos 30, and this component will be sin 40. Plus, then we will again go from here, this cos components, cos 30, cos 40, j. And this vertical component below, if you look at it, we go down as sin 30, but this is below the z, so it is minus sin 30. Now you ijk's are there. Now you just multiply it with 80, you will get F is equals to 44.53I plus 53.07J minus 40.0K Newton. This comes out to be your force F, and your position vector AC comes out to be equal to 0.555 plus 0.4J minus 0.2K meter. This comes your position vector RAC, and this becomes your force as F. So we have calculated RAC. Why? because this is A and this is C. We take the position vector RAC, and this force also, which was given in scalar, we have because we have to have a determinant in ijk, we transform this force of 80 Newton into respective Cartesian force, which was basically 44.53 I plus 53.07 J minus 40.0 K. So RAC cross F is there for us. Now we can simply determine the moment of this force about this point A, because we have position vector RAC. Now you insert the values of MA is equals to RAC cross F, and we get it as IJK. What was RAC? 0.55 plus 0. IJ was 0.4 and K was minus 0.2. What is FI components? 44.53. J components for the force 53.04, and K component was minus 40. You put it into your determinant and you solve your determinant to get MA equal to minus 5.39 I plus 13.1 J plus 11.4 K Newton meter, and this is your movement of this force F about point A. Okay, so you understand it. Again, just to give you an extra tip, numerical comes exactly like this, same values, but I can ask you to calculate the movement of this force about point A. No about point A, but calculate the moment of this force about point B. If I say you calculate the moment of this point B, now how we will solve it? Again, this F will still remain the same. It will be the constant. Means you have to calculate the values in a similar way. If the force is 80 Newton, so then for RAC will be different. We will replace this RAC with what? If he is interested in the moment of force about B, we will replace this RAC with what? We will replace it with RBC cross F. So that movement at B, then this formula will also change. It will change from MB is equals to RBC cross of F. Okay, and MB is equals to RBC cross of F, and again you will insert the values of RBC over here instead of RAC. F will still be the same. No, if the magnitude is 80 Newton and these angles are the same, so we will exactly put the values like this, and we will solve the determinant to get MB equals to RBC cross F. That is another problem, it can come. And if we say across A movement of it, then exactly you have to follow this approach. So just a tip to solve the same question with the movement at B to calculate the movement about this point B. Let's go to another very important numerical.